Welcome to this explainer. Today we're diving headfirst into a high-stakes, multi-billion-dollar scientific quest to measure the universe's absolute most elusive entities. We're talking about a recent breakthrough in physics that honestly feels like it's straight out of a sci-fi novel, but it's happening right now, deep underground. I mean, how exactly do you weigh a ghost? Because in the weird and wonderful realm of particle physics, that is quite literally what scientists are trying to do right now. They're trying to measure the mass of something that is nearly massless, carries absolutely zero electrical charge, and just effortlessly glides right through solid matter without leaving a trace. It's an almost impossible puzzle, right? But as you'll see, a massive new project in China is rapidly closing in on the answer. Section 1. The giant underground sphere. To understand how we actually catch these ghosts, we've got to look at the sheer mind-boggling scale of the machine built to do it. Meet the Jiangmen Underground Neutrino Observatory, or JUNO for short. This is a $300 million scientific marvel. At its core is a massive acrylic sphere, 35 meters across. To put that into perspective, that's roughly 10 stories high. Inside that sphere, 20,000 tons of a specially formulated light-generating liquid. And here's the crazy part. This entire subterranean setup sits exactly 53 kilometers away from a complex of nuclear power plants. It just sits there, perfectly silent, waiting to catch invisible particles streaming out of those distant reactors. And wow, is this massive investment paying off already? Yifeng Wang, the spokesperson for the 750-member team, noted that they started getting high-quality physics data almost immediately on the very first shot. Just think about this. With only 59 days of data, the JUNO researchers have already reduced the uncertainty on two key scientific parameters by a third. That is incredibly fast progress. Section 2. Meet the ghost particles. So we've seen the giant machine, but let's zoom all the way down to the quantum level. What exactly is JUNO hunting? They are hunting the neutrino. A neutrino is one of the fundamental building blocks of the universe. It's nearly massless, has absolutely no electrical charge, and it almost never interacts with normal matter. Get this, you could put a block of solid lead a light year thick in front of a neutrino, and it would likely just pass right through it like it wasn't even there. To really wrap your head around how pervasive these ghostly little things are, look at this number: trillions. Right now, as you're sitting here listening to this, trillions of neutrinos are zipping straight through your body every single second. You don't feel them, they don't do anything to you, but they are constantly raining down on us from space and streaming out from the center of the Earth. Now, what's kind of fun here is that these particles actually come in three distinct types, or what physicists whimsically like to call flavors. First up, we have electron neutrinos. These are pumped out by the sun and nuclear reactors. Second are muon neutrinos, which rain down when atmospheric cosmic rays strike the air, or they're cooked up in particle accelerators. And third are tau neutrinos, originating from the decay of massive, rare tau particles. For JUNO's specific mission, the detector is laser-focused on catching those electron antineutrinos gushing from those nuclear reactors 53 kilometers away. But hold on, because here is where the quantum realm gets completely bizarre. These flavors, they aren't fixed. A neutrino actually has no definite mass of its own. Instead, it's a quantum combination of three different mass states. Think of these mass states like intermeshed gears of different sizes all spinning at different speeds. So as a neutrino zings along at near the speed of light, these gears turn, causing the particle to literally morph or oscillate from one flavor to another. An electron neutrino can actually evolve into a muon neutrino and then right back again. It's a constantly shifting puzzle. Section 3. Catching the invisible. So if they're practically weightless, totally invisible, and constantly shape-shifting, how in the world does JUNO catch them? It comes down to a very precise four-step chain reaction. Step 1. Out of the trillions passing through the detector, very, very rarely, an electron antineutrino will score a direct hit on a proton in the liquid. Step 2. That tiny collision creates a positron, which travels just about 10 centimeters. Step 3. As that positron moves, it gives off a minuscule flash of light, and the total energy of that light precisely reveals the energy of the original neutrino. And finally, Step 4. To actually see that microscopic flash inside a 10-story dark sphere, JUNO is lined with exactly 43,183 phototubes. And get this, the team couldn't even buy sensors sensitive enough for the job, so they literally had to invent a brand new kind of phototube and build their own factory just to manufacture them. All this custom, cutting-edge hardware is hunting for one incredibly specific mathematical clue: an energy spectrum. By measuring these tiny flashes with an unprecedented 3% precision rate, which is twice as good as anything before it, Juno charts out this energy spectrum. When the neutrinos first leave the reactor, their energy graphs like a big, broad peak. But after traveling 53 kilometers to Juno, that weird oscillation we talked about flattens the peak out into what looks like a flat mesa. And right on top of that flat mesa, tiny, tightly spaced ripples. The exact shape and shift of those ripples hold the mathematical clues to solving the mystery of their mass.
Section 4. Unlocking Cosmic Secrets.
Let's step back for a second and look at the big picture. Why are physicists obsessing over the shape of these tiny energy ripples? It boils down to something called the mass hierarchy mystery. See, we know two of these mass states are pretty close together in weight, and one is the odd one out. But we don't know the order. Option A, maybe there are two light states and one heavy one. Or option B, there's one light state and two heavy ones. Since you can't just put a neutrino on a tiny scale, figuring out whether we live in an option A or option B universe is the ultimate audacious goal of the Juno project. You might be wondering, okay, why does this mass hierarchy actually matter to us? Well, solving this is basically finding a master key for modern physics. As physicist Patricia Valle points out, pinning down this ordering could finally tell us if the neutrino is its own antiparticle, which might explain how they get their tiny masses to begin with. But it goes way beyond that. It would help astrophysicists finally decode the mechanics of how supernovas explode. And it could unlock the deep secrets of how our galaxies and the entire universe evolved over billions of years. It's a huge deal. Section 5. The Global Physics Race. With stakes this incredibly high, you can bet the global scientific community is watching this extremely closely. Because of those tantalizing ripples already showing up in just the first 59 days of Juno's data, theoretical physicists like Patrick Huber at Virginia Tech are super optimistic. He says that Juno hitting its massive goal is, quote, now just a matter of time and collecting the data. Because make no mistake, this is a full-blown global competition. Juno is online right now, actively collecting this high-quality data. But waiting in the wings are two other massive projects. Over in Japan, Hyper Kamiokande is set to begin taking data in 2028. And in the US, the Deep Underground Neutrino Experiment, or DUNE, will receive its first beam in 2031. Now, physicists agree that once DUNE is fully online, it'll be able to determine the mass hierarchy as clear as day. But 2031 is still a long way off, right? So for now, Juno has a very significant head start. It really makes you step back and marvel. We are living in an era where it literally takes a 20,000-ton sphere of liquid and tens of thousands of custom-invented sensors just to catch a fleeting glimpse of the universe's most elusive ghosts. Juno is right on the precipice of finally ordering the mass of neutrinos. But it leaves us with such a profound question. Once we finally map the inner workings of these quantum ghosts, what other hidden mechanics of the cosmos are they going to whisper to us?